reproduction regime. Some region starts rolling classically.
What does rolling mean?
Evolving, the scalar field evolving down the hill. It's not. There's no angular momentum.
This is the thing that will cause it to eventually stop inflating when it goes
Yes,
to the bottom.
that's the key point.
To
Yes.
get to the kind of universe we have now.
Right. So this has a chance of becoming the universe we live in now.
Has it stopped inflating actually?
What is it?
Do we believe that the universe? I mean,
Yes. So all of this. So this is non-inflation, and if you don't have this, you don't have any successful theory. Radiation domination, matter domination. If you don't have that, you don't have nucleosynthesis. You don't form structure.
It's inflation elsewhere, but not in our part of the universe.
It better not be our part of the universe.
So
Yeah.
it's not like.
And yeah. So you have this picture. Different regions start. I don't want to. I'm watching the time, and it leads to this very confusing picture where you have eternal inflation going on most places and little pocket universes showing up all over the place. I think if you're feeling confused by this picture, that's probably just an accurate thing. I choose different zooming. Eventually it reheats. Radiation era. Let me just list. So eternal inflation is a very confusing thing. I want to validate it. And I'm just going to list some features again. Most of the universe is always inflating, not our observable universe, but most of the meta picture is always inflating. There's no sign that it's going to stop, so it leads to an infinite universe in that sense, with infinitely many pocket universes, since it doesn't stop. The self-reproduction phase lasts forever, globally. Inflation seems to take over the universe, and heuristically to some people, not to me, but to some people, that makes it seem like it's a good theory of initial conditions, because you have some little start to inflation, and the next thing you know, it's taken over the universe, so who cares exactly how it started? That's a very loose kind of thinking, but that is how a lot of people think. So I'm putting it out there. I don't like that way of thinking, but I'm putting it out there.
I didn't quite get the argument. Why doesn't it stop everywhere, this inflation?
Because more volume is created. So everywhere is a dynamical thing, and every bit that's up there is creating more volume faster than it's. So you depart from self-reproduction at a rate, at some mathematical rate given by your ability to fluctuate down far enough the potential to start rolling classically. Meanwhile, you create more volume at a rate that's faster in this regime. So that's what dominates. You need to, so you have infinitely many pocket universe, so you need to regulate infinities to make predictions. You typically use a cutoff. One illustration of the kind of issues that show up is that if you choose a time cutoff, which naturally cuts off infinities, then the most recently produced pocket universes are exponentially favored because they're produced in a larger region. Then you can talk about the young universe problem, end of time problems, so this leads to problems with interpretation. And one of the things you find people doing is instead of making predictions for data as I've been claiming you do, people are asking, well, what kind of measure do you need to put on this situation to fit the data? So you've reversed. In many situations, you see people doing the reverse of what I just claimed we were doing. And then this incredibly provocative statement, Alan Guth says, anything that can happen will happen infinitely many times. And if you think that your control of predictive power is based on counting arguments, then this is like saying, we're totally screwed. And this is what really gets other people's hackles up. And not Alan's, but other people's hackles up. And that's kind of where we are. There's some comments. I don't believe in infinity, so I've got some issues with that I've written about. If you believe in a landscape, even a small one, or a string theory landscape of 10 to the 500 vacuum, then this is going on, and each of these 10 to the 500 vacua, although I once showed this slide at Stanford, and Steve Schenker said, "Oh, come on, 10 to the 500 is nothing compared to infinity." So by that point of view,
Of the first 3 points,
yeah.
would you say they're relatively robust against whatever measure you pick, or is there some measure of dependence for the first 3 points?
I think they're all really sloppy, so I'm not going to. I think the whole thing is too sloppy, and this is what I. So one of the things that I first thought was an even greater disaster for eternal inflation was this point that Don Page made several years ago, where he pointed out. So what you have in this eternal inflation is this notion that you're going to have many pocket universes that could be this universe, so you don't know which universe you're actually in, and you might have pocket universes that fit all our current data but have different predictions for future data. So to predict future data, you need to know the probability that you're in one or the other of these things. And Don Page pointed out that you actually quantum mechanically can never make a prediction of, you cannot assign probability to that. That is a technical thing about quantum mechanics. I can show you with a 4-state system on the board during the break. It's a technical result. And at first I ended up writing a paper because Don Page and other people have taken a very lax view of that and think they can fix that in some simple way. I don't think so. I wrote a paper with Dan Phillips about that a while back. And at first I felt that this was really going to kill eternal inflation. But what I ended up feeling after thinking more about it was it's actually what this lesson is, at the fundamental thing, is that counting arguments aren't always a way to access concrete ideas about probabilities. Sometimes they are, sometimes they aren't. And so it's actually softened me up toward eternal inflation. It doesn't mean I think it's all resolved, but this seems to give me a glimmer of hope that maybe there's a way to make more sense of it than it seems the way people tend to talk about it. So I changed it to a green color to express hope. Okay, can I have 5 more minutes?
Yeah.
Okay, so very briefly, an alternative to eternal inflation. This is connects with a lot of my own work. So you can make various holographic arguments. I'm not going to make them here. I'm just going to say that you could ask, why do you think it's okay to extrapolate the effective field theory, the many, many orders of magnitude I did, all the way back to eternal inflation? There's other arguments that maybe effective field theory breaks down much sooner. So you sort of have a breakdown of the theories that are describing this already here. It keeps you from going back to eternal inflation, but it also, some of these arguments really say you get just enough inflation to describe the universe, and maybe some of the features you see here are actually reflecting this weird, unknown, non-effective field theory description that's back there, and maybe the emergence of space. I think I've said all this stuff. It has benefits in terms of measures and tuning issues. So one of the things I've done is say, well, let's make a model. Once you have such a short period of inflation, you might be seeing the very beginning, and we've made a phenomenological model for what some things that might be a little bit different from the standard assumption, and it gets these interesting features, which you can barely see on this curve, but we're in the process of checking. There are some strange wiggles in the CMB data. So if this theory fits the wiggles better than a flat spectrum, that's really fun. I wouldn't quite know what it means, but that's great science, is you get some provocative new signal and you've found it and you can connect it with some theoretical ideas anyway. So we'll see what happens with that. Stay tuned. And then further thoughts. So what happened before inflation? This is where we need a meta theory, nothing to do with God necessarily. but just how do you know, if you really think you're solving tuning problems, what are you comparing it with? How do you say, it is something special to start inflation, so is that more special or less special than choosing curvature just to be zero, or choosing a spectrum perturbations just like that, or choosing Neil and Paul's favorite model, or whatever if you're trying to say something's better than something else, you need, a scientist needs a technical way of doing that, and we don't have it. All we have is priors.
Do you need to answer that question if you believe in internal inflation?
Yes. Yeah, in fact, one thing I'll say is, so there's this loose idea that, it fills the universe, so it must be, it doesn't matter when it starts, but you should quantify that. And the one place I've seen where you can quantify that, the bigger the volume is, the less likely it is to fluctuate up there in a way that that's bad for eternal inflation. So yeah, we need a meta theory to say that starting eternal inflation is. So I totally don't accept that loose argument, and I want to see a technical calculation that says yes, this is, basically the ability to have eternal inflation means that's what the universe is really like, and I don't think we have that theory, and so we don't have a good one so far. I need to take a dig. So here now I'm letting my hair down and joining the mud wrestling. So the world is full of people who just want to believe inflation and they want to dismiss these meta questions. And here's a meta theory that's just wrong. You say, here's the inflaton potential. We know we can't let the scalar field go too far out. So we sort of equipartition. We say, well, could start out here, could start out there, could start out anywhere. So there's some chance it'll start inflating, and then inflation takes over and everything's fine. And this is a very popular way of thinking. But first of all, when you release this energy by going down, this is all happening in the homogeneous field space. So when you release this energy, there's lots of other energy you can put into non-homogeneous degrees of freedom. So this is suppressed. And furthermore, when you try to do some gravitational arguments, you get further exponential suppression. People make arguments about people. I like the term temporal provincialism because it means because we're used to having an arrow of time. We're used to start inserting fine-tuned initial conditions to give us low entropy one way or another. And these sort of arguments are rife with temporal provincialism, inserting some tuning along the way. So I just don't believe. So I think that's not a meta theory. That's really weak. And I emphasize that you even just standard Big Bang inflation with correct initial conditions is a competitor in this world unless you really say otherwise. I remind people, this is sort of the first thing I drew on the board on Monday. Inflation seems like it's weak in some sense, but geez, we have equations to solve and we can put curves through the data, so maybe we should lighten up and just have fun, which is what a lot of my colleagues just want to do. We have consumers of inflation who are busy donning their protective gear and building amazing satellites and collecting amazing data. And then there's weird people who wonder if you ever should explain the initial state of anything, which is sort of where we are. And in the meantime, the people who build their satellites get to have all this fun thanks to inflation. So I'm back to the conclusions. Oh, geez. So I didn't write my priors because it's sort of this evolving thing. What I would say is a lot of my career I've really tried to hold people to the idea if you say you're solving tuning problems, you really should be solving tuning problems, and that's been frustrating because we're not actually. I don't think we're really solving tuning problems yet. And it looks really hard to do. So that's been quite a burden to carry. And I actually have, I have cooked up some, like, here's what it would be like if you could solve tuning problems, but I don't know if that's realized. And so, on the other hand, I sort of in the mood these days to lighten up a bit and just say, but geez, we do have a way of mapping something we really believe from quantum field theory, which is the quantum vacuum, and splattering it across the universe. And compared to not having any idea where the initial conditions come from, that's something. And we should wrestle with it and see what to make of it. And also even in this work I'm doing now, where there's these subtle signals that we might see, it's, you know, inflation is it's the most powerful microscope in the universe. It's taking these tiny properties of the quantum state and splattering them out there for us to observe. And that's a cool thing, so we should have fun with that and not just spend all our time wringing our hands about what tuning really means and whether we're solving it. So that's where I'll end. Thanks.
So if I walked into your office and there were 3 or 4 like pencils of different shapes, however many problems you think inflation solves, they were all balancing. And you said, well, maybe there is a pencil straightening force that all it does is straighten pencils. And it happened at one time, and that's all it ever did. Would that be, I'm seriously talking about the pencil case here, obviously with implications, but seriously, in this case, would that be a useful predictive, would that be a theory more than the theory, we don't know, the pencils just seem straight?
So this is exactly the wall.